So let's look at the future of digital trust, and especially around two main areas of zero-knowledge proofs and homomorphic encryption. With zero-knowledge proofs, we'll look at methods such as the feature me method, discrete log equivalence, ZK snarks, and other methods. And then in homomorphic encryption, we'll be able to understand how we can actually encrypt data and still process with it. That will be around a method called fully homomorphic encryption. But before we do this, let's have a quick overview of cryptography. The main method that we need to understand here is the usage of public key encryption. So these are some of the actors that we have within cybersecurity. We have Bob and Alice, and then we have our adversaries, Eve and Mallory. In this presentation, we'll be focusing in on two of the actors known as Peggy and Victor. Peggy is the prover of something, and Victor is the verifier. When it comes to hashing methods, then we have different sizes of hashes, 128-bit, 160-bit, and 256-bit. MD5 shouldn't really be used because it has a relatively small hash method and where we can create a collision fairly easily. SHA-1 is a bit more difficult to create a collision, but it is certainly possible. The green ones here are the hash methods we should be using: SHA-1, SHA-256, SHA-512, SHA-3, and so on. And if we need a variable length hash, we use these XOF or extendable output functions. The most basic method that we have for encryption is symmetric key, and that's where we use the same key to both encrypt and also to decrypt. Typical methods here are CHA-20 and AES encryption. We can enhance our symmetric key encryption with using authenticated encryption with additional data, and with this we add in extra data into the encryption process, which is then used and as part of the decryption process. We use the same shared key and we add a salt value, and we send the ciphertext along with the salt value and a tag which will identify the authentication of the cipher. Typical modes here that we have are GCM, CTR, and CFB are AEAD methods. But we can also use CHA-20 with Poly 1305 as a method here. For key derivation functions, we have a way that we can take some secret and then generate an encryption key, typically with a salt value here too. If Alice has the same secret and salt value, then she can generate the same key. This is known as a key derivation function, and one example of this is an HMAC key derivation function, or HKDF. We can also sign messages using the symmetric key. In this case, we take a hash of the message and sign it with a shared secret key between Bob and Alice. So this creates an HMAC in this case, and then that is then compared against what's received along with the secret key, so that we can verify the sender of the message and also that the message hasn't been changed. But the main thing that we'll look at in this presentation is the usage of public key or asymmetric encryption or asymmetric methods. With this, public key encryption is typically used to encrypt data with the public key and then decrypt with the private key. We can also use it for digital signing, and in this case we take the private key or the secret key of the key pair and then digitally sign, and then the public key is then used to verify. Okay, so it's two main methods that we use for public key encryption, and one is encryption with the public key, and the other one is signing with the private key. So this leads us on to digital signatures. With this, we can take a hash of the message and then we will generate the signature using the private key, and then it's the public key that's then used to be able to verify the signature. One of the most popular signatures and increasing in its scope is ECDSA. That's elliptic curve digital signature algorithm. In this case, we use a private key along with a nonce value to create a signature, and then that's then verified with the public key of Bob in this case. Okay, so that was our introduction to cryptography. Now what we'll do is have a look at some of the zero-knowledge proofs. The examples are available at these two links here. So a zero-knowledge proof is a little like Peggy being sent into a secret cave, which has an opening that will open when Peggy, if she knows the secret, will be able to open up the passageway. In this case, she could go into A and appear out of B. The zero-knowledge proof means that Peggy needs to prove to Victor that she knows the secret phrase to open up the gateway between the two routes. In this case, she will go into the cave, and then Victor will ask her to appear from one of the outlets. So let's say she appears out of the correct one. If Victor says appear from A, then she can. If she appears out of A, then she has probably a 50-50 chance of getting that correct. If again she goes into the cave, and this time she also appears from the right route, again she has a 50% chance or a 1 in 4 chance of getting that right. So every single time that Peggy appears from the correct route, she proves to Victor one bit more that she actually knows the phrase. If for any reason that she can't appear out of that route, then she will not be able to prove that she knows the secret. So zero-knowledge proofs is all about proving something that's secret without actually giving away what that secret actually is. So in an interactive zero-knowledge proof, we will register something about the knowledge of a secret. In this case, it's X. It might be our private key or our date of birth or our age or even our gender. That will be registered with Victor. Then when Victor wants Peggy to prove something, then he will ask her to create a proof. Based on the secret X, then Peggy should be able to create the proof that Victor, the verifier, can actually verify. So a typical way that we would store passwords, for example, is that we would hash the value along with a salt value. Unfortunately, with this can be attacked by rainbow tables, brute force, dictionary attacks, and so on. A much better way would be for us actually to register some proof value that can be checked against a future a better way is for Peggy to register something about her secret, and then for Victor to challenge her with a puzzle that only she can solve because she knows her secret value. And this was solved with this paper here through Amos Fiat and Audrey Shamir, and they outlined a method that allows us to be able to identify ourselves without actually revealing our secret. The way it happens is like this. So in this case, we'll use discrete logarithms, and this is quite popular in research papers to define the methods. These days, we typically use elliptic curve methods, and I'll show how you convert from discrete logs into elliptic curve methods in a little minute. But it really comes from the way that discrete logs work. If we take g to the power of x to the power of y, that becomes g to the power of xy. We also bring in what's called the mod p, where p is a prime number. And with this, we can still perform all our mathematical operations and they will still work. So in this case, Peggy has a secret, her password. She takes a hash of the password and that becomes the value of x. Then she takes g to the power of x and defines that as a value y and takes mod p. That is then sent over to Victor and Victor can now store that. It is not possible for Victor to find out the value of x, or it's very difficult, even though he has the value of y and p. First, Peggy creates a secret value v, then takes g to the power of v mod p and sends it over to Victor. Victor then creates a challenge, a random value c between 0 and p, and sends that over. Now, Peggy will calculate v, this value, minus c times x, and takes a mod of p minus 1. Then I can send that value over, and where Victor now computes g to the power of r, this one, times y to the power of c. And this should equal the value here that Peggy actually sent. The proof is here if you want to see it, and there is the proof over here. G to the power of r becomes g to the power of v minus cx, and y becomes g to the power of x to the power of c. That becomes g to the power of xc. We have that value here. And then when we're multiplying, we then add the indices together to give us this. And then these two values will cancel and we end up with this here. Okay, so in this way, Victor can challenge Peggy with a secret. When Peggy wants to log in, she just sends some sort of random value that she's generated, and then Victor will be able to prove that it is still Peggy. In this way, this is what's called an interactive random oracle access. Both Peggy and Victor are creating random oracles, or random values, to be able to create the proof. So let's look at how we convert from discrete logs into elliptic curve cryptography. So in discrete logs, we have the form of g to the power of x mod p, but in elliptic curve cryptography, we will have a value of xg, where we multiply a scalar value x by the base point g. So we define that as xg, and it's basically taking the base point g and adding it x times. Okay, so initially we will create our x value, which will be the scalar, and then we'll multiply that by the base point to give us this public value that's sent over, and then Victor can store this. When Peggy wants to log in, she will receive the value of c from Victor. Peggy will generate her own v value here, and then calculate, just like we did here, a scalar value of r. She then sends the value of r and vg over, and then just like we have here, then Victor will actually do the proof here. So they are equivalent, and these days this is the methods that we typically use when we're actually computing the zero knowledge proof. But obviously there's an overhead here in terms of Peggy having to receive the challenge from Victor. So an proof method is what's called a non-interactive zero-knowledge proof. In this case, again, Peggy generates V, and then she creates a hash, and this is what the Fiat Shamir paper outlined. It's a hash of G, VG, XG, and Peggy's user ID. That will then go into the C value just like before of it, and then Peggy will send over the value of R and VG that she's actually created as a random point. Then it's fairly simple. Victor will be able to recalculate the value of C from G, which he knows. He's received VG. He knows XG from here, and he knows Alice's user ID. So once he computes that, he basically just puts that into there, takes the previous value of XG and of RG here, taking the value of R and then multiplying it by the base point G, and he will check that that is equal to the VG value. The proof of this is here if you're interested, and hopefully that should all work out. So the great advantage here is that Peggy can generate her own proof and then send that over to Victor, and Victor can now check it against the public value or the value that's been registered for Peggy. So let's look at an example of this. So here we are, and we're using the Bitcoin curve here, SEP 256K1. Okay, and we have a value here that we need to prove. And we can see here is the XG value, which is the point on the curve. The V value is what Peggy will generate as a random value. And then she computes VG, which is another point on the curve. After this, Peggy can work out the value of R. And then we can compute a value of C, which is obviously the hash value for the challenge for Peggy. When we're doing a check, we can actually just check that back, and then we can actually prove that we have that Peggy actually knows the original value. Okay, so it's fairly simple in its actual approach here. Another method that we can use is what's called a discrete log equality method. In this case, what happens is that if Peggy has a value of X and a public value of XG, she can actually produce another point on the curve with a new base point of H. And then Victor will be able to prove that the value of X is actually the same without actually revealing it. So this is useful in areas of proof of identity, that actually Peggy can actually produce another point on the curve and prove that she has a specific private key. So the method is here. We create 2 points on the curve, and just as we did before, we do our non-interactive zero-knowledge proof calculation, and we just compute the values as before. The checks become slightly different now. We check against 2 points, and then if the points are proven, then we know that Peggy knows her secret or a private key of X. Okay, so let's have a quick look at example here. Okay, so here's a value of X. We're taking a G value. This is the discrete log. This is the elliptic curve method. So we have our X here, there's the G and the H, and we're calculating the points that we have here. This is the challenge and then the response here. And in this case, we can actually prove that Peggy actually knows her secret value of X. Another method that allows us to be able to hide information and hide identity is what's called a ring signature. In this case, we can have a group of entities, and where one entity in the group actually digitally signs a message, but where it's not possible to know which one of the group actually signed. So a ring signature is something that brings anonymity, unforgivability, and also collusion resistance. Basically what happens is that we take public keys from all of the entities in the group, but we sign the entity, or the signing entity will use its own private key to be able to create the signature. One of the methods that's been created for this is what's called the Borromean ring signature. And perhaps we can have a look here. So this is an example here of us creating our signature, and where we can actually prove the signature depending upon different signers. Another zero knowledge method is what's called an accumulator. In this, we can create a fixed length accumulator, and then where we can add data into the accumulator using the private key of the entity. We can also remove the data if we require. After this, then Alice can create what's called a witness that a certain value is in the accumulator without revealing any of the other data that's in there. Then, using the public key, Bob can then verify that that data is in the accumulator. Okay, so if we look at an example here. So we have 4 words that are in the accumulator, and then we can actually prove those values are actually in there. A powerful method that we can use is to have what's called a range proof. So range proof allows us to be able to take a minimum and a maximum value and show that our secret value is within inside those ranges. So this might relate to someone's salary. We might not need to know the actual amount of the salary, but we need to know that the salary is between 20 and 30,000 euros. For this, we can then create a range proof that Victor can actually check against. One of the most popular range proofs is what's called bullet proofs, and produces a small range proof verification. And one of the applications of this is within Bitcoin, and where we can mask all of our transactions for the money in and the money out, and then we can use a range proof to show that in this case Bob has enough Bitcoins to pay Alice. Basically, we just need to know that the unspent amount of Bitcoins is greater than what he's actually spending on the current transaction. So bulletproofs are a powerful method that allows us to be able to perform that operation. And there are several different types of range proofs that we can actually get, but bulletproofs are one of the most popular methods. A method that's more for hiding rather than a zero knowledge proof is what's called a Peterson commitment. In this case, we use a blinding factor on our commitment, so that it is not possible to know the value of the commitment that we're committing to. But at some time in the future, Bob can unblind it by revealing the factor. But we can also compute transactions or the total value of transactions because of this blinding factor. So with this, we might have 2 points on the elliptic curve. In this case, we have 4 bitcoins. This would normally result in this transaction here, but then we have a blinding factor which is then added on to the transaction. So it shouldn't be possible to actually see what the value of V and VH actually is, because we would have to know the value of R and G. A more complex method of zero-knowledge proofs is what's called ZK snarks, and that's defined by zero-knowledge succinct non-interactive argument of knowledge. For this, what we have is we have a mathematical function in which we have a public value entered, and then we have our own private input, which is the actual secret value. Then the ZK snark can tell if this is true or false. If the value that's entered in the private value is not correct, then we will get a false for it. One example is to take an equation such as this, and we should be able to prove that we know that the answer to this is 3. For this, we create our zero-knowledge proof and prove that we know that the answer to this equation is 3. For this, we actually create what's called an R1CS file, and this allows us a very quick checking that the answer is actually correct and the value that we've actually given. For this, we take our equation and then convert it into a form, which can then be read in and converted into this R1CS file. With this R1CS file, it's fairly easy for us then to be able to check that the answer to this is correct. So if we want to have a look here, this is the example process that we have here. Here is an equation that we have, and we represent this as some sort of program with a function, and then we create what's called an R1CS file. So this is the file that's then used to be able to create what's called a witness for the actual proof of knowledge. So let's look at fully homomorphic encryption. I appreciate some of the concepts here might be a little bit difficult to take in first time, but really I'm just trying to provide an overview of fully homomorphic encryption. So let's look at fully homomorphic encryption. So some of the terms in here might be a little bit difficult to understand initially, but it's really just an overview of some of the basics involved in the usage of FHE. So let's do a little bit of a background, and this may be a little bit tough to take in initially, and probably needs to be studied a little bit. So there are 2 main methods for fully homomorphic encryption. One is an asymmetric method where we use a public key and a private key pair, and then we encrypt with a public key, and then we can process with encrypted values, and then we decrypt with a private key. We can also use symmetric key where we use the same key to encrypt and then also to decrypt the answer. Asymmetric is typically used because it's easier to keep the the private key secret. In this case, we take the public key, encrypt the values, give them to the data processor. The data processor can then process these values but not reveal the original values. And then we can decrypt with the private key. So basically what happens is that we can use any operator that we want, such as multiply, divide, add, and subtract, and so on. And we can then perform the same operation on our encrypted values. I won't go into too much detail here, but basically what we do is that we have a lattice of multi-dimensions and points in space. There will typically be over 1,000 of the 1,000 axes that we have. So we can imagine a lattice with lots of possible points, and we have a point in space. That point can then be represented as a vector. And the vector itself might be this point here. And an easy way to represent that is with a polynomial value. So this is an example of a polynomial here. And these polynomials just make it easy for us to be able to add and subtract and multiply and so on. We sometimes also have to find the inverse of a polynomial. So there is a method of defining what's called the inverse of a polynomial mod p. I won't go into too much detail, but it's really just inverting something that we've done in the past. Maybe we multiplied by a certain vector. If we want to reverse that back, we find the inverse of the polynomial and then perform the multiplication. And really, the lattice cryptography is all based on what's called learning with errors. With this, we have a matrix A, and we have a secret vector S, and we add on another error vector to produce our output vector. Okay, so this is the matrix we have here. This is our secret key, and this is the error that we're adding here. We also perform a mod operation, mod p, on this to be able to limit the values that we get as a result. Okay, and it's this method that's actually a difficult method to be able to discover the secret key, given that you actually know A, E, and B here. So the four main generations that there has been was the original Gentry method, which used integers and lattices. Then a major step forward was with the BGV and BFV methods, which allow us to be able to process using this learning with errors approach using integer values. Then the third generation brought in the usage of Boolean circuits, where we can actually use any Boolean logic that we have, and any mathematical function can be broken down into and or gates, and that's known as DM and CGGI. And then finally, the fourth generation is where we can operate on floating point values, and that's with CKKS. Okay, so here's our homomorphic encryption here. We're using the public key to encrypt, and then the private key is then used to decrypt the result. We can also have the value sent off-site into a secure enclave, where the private key is only stored in the enclave. And the exciting thing is that we can also have deep learning and machine learning processing, where the encrypted values can go into the machine learning method, and then our output is given, which can then be decrypted with the associated private key. And this gives us a possible future architecture where on a gateway or an edge node, we can have some homomorphic encryption where the data could be processed within that gateway and then sent back without the need to go into the cloud to be processed. So let's have a look at some basic concepts and some code. Some of the code might be a little bit difficult to interpret, but really it's just there to maybe show you how the the mechanics work. So there are many libraries that we can use. One of the popular libraries from the past was created by Microsoft, and that's the SEAL library, not as much used these days. In this case, we'll mainly use the OpenFHE library, which is an open source library, and that was based on the Palisade library from the past. Okay, so as I said, the main methods that we'll be using: BFV and BGV for integers, CKKS for floating point values, and DM and CGGI for Boolean circuit evaluation. Unfortunately, what happens is that we have vectors with a little bit of an error, but then when we multiply these vectors together, then the errors are going to start to mount up or multiply. So we need to be able to clean off the error every so often. And this is quite an overhead within homomorphic encryption, and it involves us implementing what's called the bootstrapping process. We take an encrypted version of the private key, and then we're able to clean off the errors that's been generated inside our processing. Typically the multiplication, and whenever we see multiplication, that's the main place the error is added up. Another thing we can do is that we can have a number of slots, and we can have the same function, and then it can actually run almost like in parallel. So we can speed up our homomorphic encryption processes if we have the same function that needs to be conducted on different data slots. So the main parameters, and I appreciate this may look a little bit confusing at the current time for you, but it at least outlines some of the core parameters that we actually use. So with this, we have what's called the polymodulus degree, and that's basically the number of accesses that we have inside our lattice. The more of these that we have, the better the accuracy will be, because we can represent more bits in the lattice. But unfortunately, the performance will actually drop as we keep increasing them. So these are typical values that we use, and they must be of a power of 2. The plain text modulus will limit the size of these polynomial values, and we do perform a mod p operation to be able to limit the actual values of the polynomials. Again, that will affect our accuracy overall. Okay, and this is the CKKS example here, and we can see here is the polynomial modulus degree. Okay, so this shows a basic example here. There's the plain text modulus value that we're setting here. We also define what's called the multiplicative depth. That's the number of multiplication options that we're going to have. In this case, we're creating our key pair here. And with this will create our public key and our private key. Okay, so this is examples here again. So here's an example of us using a method to be able to perform the evaluation. So we can see here the range of evaluation methods that we can actually have. So we can have an add, multiply, and so on. Okay, so we can see here is the encryption of the data into our ciphertext using the public key, creating ciphertext here. Now we perform the homomorphic encryption. So in this case, we're taking the two ciphertext values together, and then we're actually creating the result. It says cipher multiply, but it's actually add in this case. Okay, and then we decrypt using the private key here. Okay, we're taking the ciphertext, and then the output will be placed here. Okay, so if you think about it, what we're really doing here is that we're encrypting our data. We're converting our values, our integers in this case, into polynomials. We then encrypt with the public key these polynomial values. We then perform our operation on the ciphertext, and then we decrypt with the private key here. Okay, so here's an example here of multiplying two numbers together and also adding. So in this case, we're just performing different types of evaluation here on the ciphertext, and then we can actually decrypt the result using the private key here. Okay, so there's the that's us encoding the values that we have. That's us encrypting them with the public key. That's our processing, and here is our decryption here. Okay, so I've placed examples on the web here if you want to try them out. You can also implement these examples with Python. Okay, so as I said, we can also use this batch mode where we might have multiple slots for the same operation but with different values. And this is an example here where we actually are creating, if we can see, a square. So we're taking different values here, performing the square function, and then we'll get our outputs here within inside the slots. One really powerful method within homomorphic encryption is to use Boolean circuits. And for that, we can use the MD method. So in this case, we might have a Boolean circuit such as this, which should give us this logic out from there. So for this, we can actually use our evaluation gates here. We can see that we have an AND here between bit 1 and bit 2. That's the AND function here. And then we're taking not bit 2 here, and we AND them together here, and then we can create an OR function here for the circuit. And it's the same thing again. We basically will take we encrypt. We will then operate on the cipher values, and then we will decrypt here with the private key. Okay, in this case, we're actually using symmetric key encryption, using the same key to encrypt and to decrypt. Okay, so that shows another example. And we can actually build up fairly complex circuits, such as using half adders and to build up a full adder circuit, such as this one. Okay, and there are gates such as a MUX gate. With this one, if we have a 0, we will select A. If we have a 1, we'll select the B value. So it switches between one and the other. The majority gate will only give us a 1 if the majority of the inputs are a 1. So in this case, we've got two gates. One is the majority gate, and the other one is a MUX gate. And again, I have examples of this online that you can actually try out. A powerful method that we have inside homomorphic encryption is what's called the Chebyshev functions. In this case, we can take a standard mathematical function, such as log10, log2, or log, and then we can convert it into a polynomial format using this Chebyshev function. And once it's in this format, we can actually use it within our homomorphic encryption. So this allows us to be able to take a standard maths library and then convert it into a polynomial form that we can then use within our homomorphic encryption. We can also perform polynomial evaluations. So sometimes we might have a polynomial and we want to actually plug in a value of x into that and then perform the operation. So this is the function here that allows us to be able to do that on our ciphertext values. So let's look at some examples of where homomorphic encryption might be used. In this case, we have a hospital and a patient. We then encrypt the patient's details using the public key, send them into the cloud, homomorphically compute something, and then send it back to the hospital, and then the doctor can then use the private key to be able to decrypt. The advantage here is that the data from here out is all encrypted and any entities in the cloud can't see that data. We can also use what's called multi-party sharding, and it's possible for us to take the keys and then split them up for different parties, and then for each party to compute a part of the overall computation and then bring the values back together. This is an example here from a research paper. In this case, then we have an industrial plant, and where the data producer, we can then encrypt the values and then decrypt them back again to provide analytics. In this case, we can have a public cloud, and it's not possible for anybody to see any of the original values here. There is also another method called order preserving encryption, and this allows us to be able to use an operator such as, is this value greater than this value? Let's say that we have an encrypted value of Bob's age and Alice's age. Then we can actually find out if Bob's encrypted age is larger than Alice's encrypted age. This has some applications, but obviously isn't as powerful as fully homomorphic encryption. Another method that we can have is what's called proxy re-encryption, and this is implemented here. With this, we have something that's been encrypted with Alice's public key, so that would be Alice's private key that would decrypt it. We can then use what's called proxy re-encryption to be able to re-encrypt the encrypted data so that Bob's private key can then decrypt it. So in this case, we can seamlessly hand over something that was encrypted with Alice's public key so that it can now be decrypted with Bob's private key. This should be used with caution because there are many problems that can be caused with this. But the code here should implement proxy re-encryption. Okay, so let's look at some examples in the cloud. So in this case, we can, as we saw before, we can use a secure enclave to be able to store a private key if we're using symmetric key encryption. Otherwise, we can use a public key to be able to encrypt and then use a private key to decrypt. There are many different methods that we can actually use fully homomorphic encryption to create what's called searchable encryption. With this, it's possible for us to have encrypted values that will relate to users' IDs and so on, and to be able to compare them with an fully encrypted value and then return again an encrypted result. This was one method that was used within COVID times. In this case, we can actually take the time and the location of someone, such as Bob, and then we can encrypt them with homomorphic encryption. Then, inside our homomorphic encryption engine, we can actually compare the time differences and also the locations to find if someone was in a location at a certain location at a certain time. In this way, we can perform the operation with homomorphic encryption. A big area of usage is in privacy-aware biometrics, and in this case, we can encrypt homomorphically the biometrics for a person, and then compare it with their biometric data homomorphically, and then look at the delta between the two when we decrypt that with a private key, we can tell the difference between the stored biometric and also the one that we've just captured. Apple, at the current time, use homomorphic encryption in terms of actually locating a user and then to be able to match photographs which are close to the user. In this way, the GPS coordinates of the device are homomorphic encrypted and then compared against certain locations homomorphically. Then it's possible to then match images that are close by that region of interest and then return them back to the user. In this way, the Apple doesn't know where the user is and doesn't know the images that are getting sent back. So let's look at multi-party computation. With this, we can use what's called threshold encryption, and this splits the key into a number of shards. And then the key can be then used to be able to perform various operations. In this case, we then split the keys up, and then each party can then perform the operation, such as they want to sign a document. Each of them would create their own signature. And then to be able to, we can then just aggregate these signatures together to produce the overall signature. It is also possible to do it for encryption of data. So let's look at privacy-aware machine learning. So with this, what we have is that we can either use a machine learning model and then feed in homomorphically encrypted data and get a fully homomorphically encrypted result. A more powerful method is that we can actually train the model on homomorphic encryption so that it's not possible for the model to actually see the data that's actually coming in. So this one can be defined as a prediction service. So in this case, we have already trained the model and we then feed the homomorphic encryption in and get a homomorphic encryption back so that the cloud provider of the model doesn't see any of the data. But what's more exciting is that we can use private data to be able to train the model. Okay, so there have been many examples of this private prediction as a service where we can actually train our machine learning model on homomorphic encryption. One of the core methods that we need within a neural network is what's called a logistic function. The way that a neural network works is that we have a neuron that has various inputs into it, and then we will either fire that neuron or not based on a certain function. This is typically a logistic function. In this case, what we've got is that we have a basic mathematical formula that does this firing or not of the neuron. So here is a basic implementation of it there, and we can see that we have a function, a variable called evaluate logistic. But what we really need is matrix operations. And the good thing is that with fully homomorphic encryption, with the OpenFHE library, we can actually perform matrix operations. In this case, it is the dot product of two vectors together. Two vectors can be multiplied together to create a result. And we can see in this case it's what's called an inner product value. So then we can take something like a neural network, and a neural network is really basically taking a vector and then performing a matrix application on it. So if we can actually model our homomorphic encryption like this, then we can actually produce a neural network. And that is obviously the basis of much of our machine learning these days. So in this case, our input vector would be encrypted with a public key. We can then multiply that encrypted value with a matrix value. for the weightings of the neural network, and then produce our output, and then we can then decrypt the output with our private key. Okay, this is an example here of the code that we can actually use for this. We can see here there is the vector times matrix multiplication here for that to actually happen, and we can see it's getting done with the public key, and then it's the private key that's then decrypting the output that we saw here. So this gives us a really exciting opportunity that we can actually train or we can run prediction as a service within the cloud, but using homomorphic encrypted values. In this case, it would be a neural network. Okay, so here's an example here of us multiplying matrices together and producing our result here. Again, we're using the private key to be able to decrypt. Then when we have multiple matrix multiplications, then we can actually perform that with inside our library here. Okay, and this research paper here actually studied this using a genome study, and they actually found out that the accuracy was almost perfect in terms of the difference between non-homomorphic encrypted data and homomorphically encrypted data. Obviously, it takes a lot more processing to actually do this, but in this case, the processing preserved the privacy of the entities involved. So one method that's possible for this as a prediction as a service is that we can train a support vector machine with sklearning using training data. So typically we would take 80% of the data set that we have and then train the data on some target. Then we would try 20% of it to be able to see how successful we were. Once we think that that's acceptable, we will then output the weights and the intercepts into a homomorphic processing infrastructure for SVM, and then we can then encrypt the input data with a public key, run the SVM engine, and then decrypt the output with our private key. So I've got some examples of this on the related website if you want to give it a try. An interesting little library is Concrete ML. I think it only supports integer calculations, but the advantage with this is that we can actually use sklearn methods straight into a homomorphic encrypted engine. Okay, so I appreciate that's been a rather long introduction. There are lots of different examples on the related websites, but hopefully that's given you an overview of zero-knowledge proofs and fully homomorphic encryption. Thanks.